So have you went through this books, like some portion? This book will help you a lot in some portion of understanding, that is the linear algebra part, because I guess many of you were saying on the discourse about the difficulty that you are facing. So you can refer this book. It's a very good book. Like some portion, like maybe the 10 pages, that's it from this book. Okay, so yeah, so for the positive definiteness, the function should like, it's not compulsory, but it should, like, for example, if the function is vanishes at 0 comma 0, and it's strictly positive at all the, so I'm just focusing on the sixth week, and that is the last, like, half portion of the sixth week. Okay, I'm leaving the SVD part and I'm covering the positive definiteness and then the other parts. Okay, and then we'll move to the PCA part. Okay, I'll just give you a brief idea, and after that, if you are just going through the lectures, you'll be able to understand. I'm pretty sure about that. Okay, so now, is it clear, like, what we are going uh, to see in this today's session? Can somebody tell something, or
Yes, sir.
okay? Hmm.
Sure.
So yeah, so the other part, like, is the positive definiteness. Okay, so for the positive definiteness, I asked you about the one quadratic equation, right? So how will you tell me whether if the given quadratic equation will be going upward or a downward curve? Okay, so if the a is positive, if the a, here you can see the equation, right? Ax squared plus 2bxy and then cy square equals to 0, right? Can you see this?
Yes, sir.
Yes,
Okay,
sir.
so how do you think, how will you represent this graph if a is positive? So whether this will be like this or like this, or maybe like this. Which one is correct out of the three? For a greater than 0, for the a positive, the coefficient of x square is positive.
First
The
one.
first one.
The first one, right?
Yes, sir.
Just imagine that, if you are imagining this in the, what you can say, in the 3D plot. Okay, it's like a ball. You can imagine this is a ball, not that BALL, that BOWL. Okay, like a ball. So you'll be having the minima at this point, right? If you're getting something like, look, for example, at 0 comma 0, this function is vanishing, or the slope is 0 at this point. Okay, so this is a ball and that is going upward, right? So this is what the positive definiteness function will look like. Okay, so like this, and for all the function, for all the values, it will be, if this function is vanishes at 0 comma 0, so whatever the value you are taking, okay, in the surrounding of 0 comma 0, you'll be getting the positive value every time, right? If you're imagining this curve in a 3D plot, just imagine as a ball, and then think that the lower part is at 0 0. Okay, and if you are moving, like for example, you are moving at 1 comma 0, or maybe 0 comma 1, anywhere, if you are moving, you'll be getting the positive value, right? Correct. If you're moving here, you'll be getting some positive value, right?
Yes, sir.
Huh. So this is what I was telling. So for any, if you need to know regarding the, if you have the plot, you can directly say whether this function is positive definite or the negative definite, or you are not able to say that. If you have a function like this, the third one that I told, this function. So even for this function, you can't say anything, because for some points you'll be getting a value. If you are moving to the neighborhood, you'll be getting a positive value, and for some value it will be negative. So you can't say regarding at which point it is vanishing, right?
Yes, sir.
Yes.
Hmm. So see, in the lecture, I'll just, so in the lecture, sir has started with this one. So you have been given a matrix. I'll tell you how to generate a, how to get the matrix out of the equation that has been given. Okay. So mostly you'll be given, like, you have been given a many, maybe a function or a matrix. Okay. And out of that matrix or the function, you need to say how does that function or the matrix will behave like. Okay. So whether it is a behaving like a positive definite matrix or the function, or the negative definite or the function, or maybe some other are also there, like indefinite, or some other matrices that will be seeing in the later portion. Okay, so the first one that he's describing about, he just told you have a matrix in the form of this AB, and always remember, we are just dealing with the symmetric matrix. Okay, if you have not been given the symmetric matrix, for that matrices you won't be able to say anything about, at least the character regarding the definiteness. Okay, so if you have been not being, if you have one get the symmetric matrix, you can't say much about the character of, at least regarding the positive definiteness of the matrices. Okay, so the first point that you need to check is whether the matrix is given is symmetric or not. So you can see this here, you have been given a symmetric matrix, right? How will you check whether this is symmetric matrix or not?
Matrix is equal to its transpose.
From the elements of the matrix.
Hmm. Yeah, that's correct. So you can, um, that transpose also you can check, and then see whether the transpose and the same matrix is same or not, or maybe the element by the element also you can see. So yeah, fine. So the first point that you need to be there in your mind is whether this function, or the, not the function, the matrix is symmetric or not. I'll tell you the function also, how to get the function, or maybe from the function how will you get the matrices also, that also I will discuss. But the first point is, if you have the matrix, first check whether this matrix is symmetric or not. Okay, and now you need to see whether this is a positive definite or not. Okay, so I'll just show you one graph. Okay, so you can see this, right? This plot, you can see this is the definite. The first one is the definite, positive definite. Okay, so I was telling you this is like a ball. Okay, and that is going upward. Okay, right? You can see this, right?
Yes, sir.
Yes, sir.
Okay, and the second one is the semi-definite, and the third one is the indefinite. I'll tell you about the both other two function also. The first one is the definite. I'll just explain you about everything about the first matrix, and then we'll move forward further. Hmm. For the first matrix, if A is positive means it's going upward. Okay, if A is negative, that means this function is going downward, right? Like this, maybe like this. If A is negative, right, and if A is positive, that means it's going upward, right? So this is the first. So note, if A is greater than 0 and AB minus B square greater than 0, then both the eigenvalues, okay, this is positive, positive, and okay, so that is fine. But I'll tell you how generally we get that. So there are basic method. How will you approach if you have been given a matrices? How will you tell that whether this matrix is a positive definite first or not? Okay, so there are some method, like 2 3 method, but the best method is to calculate the eigenvalues. So the first and the best method is to calculate the eigenvalues. So if you are able to calculate the eigenvalues of the matrix, that you need to say whether this function, this matrix is behaving like a positive definite or not. You calculate the eigenvalue, and if all the eigenvalues, I am telling for the all the eigenvalues, even one eigenvalue is negative or 0, that is not the positive definite. Okay, so for all this, the compulsory what you can say, the criteria, if you are getting all the eigenvalues that you have calculated, it's greater than 0, it's not greater than equals to, if you are getting greater than 0, then it's the positive definite. Okay, is this clear?
Yes, sir.
Okay, or the second way is, so the first way I told you, if you are getting all the eigenvalues as greater than 0, then this is the positive definite. And the second is the pivot value you are getting. Pivot value you are knowing, right?
Yes, sir.
If the pivot values, all the pivot values are greater than 0, then you are then the matrix is the positive definite. And the third one is the energy that is consumed in that matrix. So A is here, the matrix for all the x, it is 0. So this
Sir,
greater than 0.
I have a
Yeah.
doubt, sir. Actually, pivot value, if all the pivot values are minus, then we can multiply -1 with in that matrix. No? All the
Mm,
pivot values are -1, -1, -1.
okay, so but for that, if you are multiplying -1, this is not the, you'll be getting a non like negative negative definite matrices, where the function will behave like a function is like a ball that is going downward. Okay, so whatever the matrix is given there,
No,
if
sir.
you are
In
getting,
RE resolution, uh, while we are decomposing that matrix to 1 0 like that
Mhm.
pivot matrix. Then
Huh.
instead of R2 minus R1, I made R1 minus R2. Then negative is possible. Na? So how we can say pivot values define that PD?
Okay, so see, for example, if you are getting uh, so if you have, see this, okay, so we are saying whatever you're saying is correct. Mm. Okay, I'll check this once and then let you know. But value this, okay, if your everything is minus minus minus. See, one way is to, you can, what you can do is, and okay, fine. See, if you are getting a matrix like this, okay, so you're telling, if you have done the whatever the that to get the pivot values, whatever the multiply, or maybe the calculation, whatever you are doing in such a way that you are able to negatify, like you are getting some minus value, and then okay, I'll check this, right?
Okay, sir. Okay.
Hmm. And one other method also is there to check whether this is a positive definite or not without calculating the eigenvalues also. What you can do is, you can calculate the determinant of each of them. Like you have, if you have got 2 cross 2 matrix, okay, so first check the determinant for first check the determinant of this 1 cross 1 matrix, that is A is positive, that is what sir has told. And then check for the 2 cross 2 matrix. Okay, so that will be what, AC minus B square, and that is greater than 0. So this is what has been discussed. So this is the another way to check whether this function, this matrix is a positive definite or not. So what you'll be doing first, you'll be just calculating the whether you'll be checking whether the 1 cross 1 matrix is positive or not, the determinant of that. And then for the second matrix also, that is the 2 cross 2, that is AC minus B square. And if both are positive, then you can say this is a positive definite. And if this is a 3 cross 3 matrix, then what you need to do, first check for the a greater than 0, and then check for the 2 cross 2 matrices, and then check for the 3 cross 3 matrices. Okay, and for each of the 3 matrices, if you are getting the determinant as positive, then you can say this is a positive definite matrix. Okay, and for all the condition, it should be greater than 0. None of them should be equals to or maybe the negative. Okay, even one is getting 0 or negative, then you can't say about you need to get, you need to go and calculate with the help of eigen values. If you are getting any, what you can say, mm, um, confusion in this method, you can calculate the eigen values. This is the one, like you can say this is the best method that you can do, is to calculate the eigen values, and I guess that will take a much lesser time also to calculate. Okay, so the one method that I have discussed is to calculate the eigen values, then the pivot values, or maybe the determinant method. So each determinant you need to calculate. The third method is like pretty difficult, because you need to check whether for all the values of x, this whether this function is positive or negative. Okay, that's the another method. Like for example, you have got any matrices A, and then what you can do is x transpose multiply x transpose and then x, and then check whether for all the x that you are putting, whether this function is greater than 0 or not. If this is greater than 0 for all the x value, then you can say this is a positive definite. But this is a pretty difficult method to calculate. So the best one is to calculate the eigenvalues. That has thus, I guess, then the starting sir has discussed about that. Okay, so the PD you will be able to see, right, whether this matrix is PD or like positive definite or not.
Yes,
Fine. So okay. Okay, similarly for the positive semi-definite, this is what the function looks like. The function will look like this. So this is the positive semi-definite. Semi-definite in the sense you'll be having a curve like a value. Okay, where you'll be getting a plane of x such that at that point the function of the value will be 0. Like you can imagine this as a valley, right? For this whole plane you are getting the value x value as 0, right? So for to get whether this function, whatever the matrices that has been given, whether this is behaving like a semi-definite or not, what you need to check, again you need to calculate the same stuff, eigenvalues itself. And if you are getting even a one eigenvalues as 0 and the other eigenvalues as positive, so the eigenvalue should be greater than equals to 0 for this condition, for the semi-definite one. So the function, the condition would be this one. So okay, so the condition is not been written here. So the condition for positive semi-definite is what? So the whatever the eigenvalues that you are calculating, not the summation. So all the eigenvalues should be greater than equals to 0. Okay, like for example, you are getting eigenvalues 1 as 0, and the second one is 1, and the second one is, the third one is 2. So this is a semi-definite, positive semi-definite. Okay, so if you are getting this one, lambda 1 equals to -1, and then lambda 2 equals to 1, whether this is a PD or not, positive definite or not, what is this? This is a positive definite or positive semi-definite?
None of the two.
None of them.
So this is not even a positive definite or not even the positive semi-definite, right? Okay, so the first condition that I told you, if you have the matrix and all the lambdas are greater than 0, then this is a positive definite matrix. And if all the lambdas are greater than, like even the one lambda is greater than 0 and the other are like positive or something else, then you can say this is a positive semi-definite, right? Okay, and the same condition you can apply for the negative definite and negative semi-definite also. What is the same that, so what would be the condition for that negative definite? Can somebody tell me from here itself?
Lambda less than 0.
Negative
Huh.
eigenvalue.
So the lambda, if the lambda you are getting is less than 0, then this is a negative definite. And similarly for this case, some lambda is 0 and some are negative, then you can say this is a positive semi-definite. Okay. So this was regarding the matrices. If you have been given the matrices, then you can say directly whether this matrix is how it is behaving, right? If you have been given the function, then how will you say about that?
So suppose the lambda is 1 and 2, then it's positive definite, right?
If the lambda is 1,
And 2,
this is positive definite.
and 1, 2, and 0, and then
1, 2, and 0, this is positive semi-definite.
okay, if there exists any value of lambda is 0, then it is positive semi-definite, right?
Huh.
Okay.
So, sir, there won't be a case where we will get positive, negative both.
For the positive and negative, we'll discuss later, like
Okay.
today itself, but we'll see how does that function behave. Okay. Till now, we have just discussed about if this is a positive or positive with some 0, or negative, all negative or negative with some 0. Okay.
Yes.
Hmm. Okay. And if you have been given the function, how will you say about the character of that? So character of the matrices corresponding to that equation. Like if you have been given any function, okay. So this is the function. How will you say about this equation? For the matrices, you already know. How will you say about the equation? So you can get the any
Positive
problem in the
definite.
form of function or the matrices. Can somebody tell me how you generally get the matrices? So you'll not get the exact matrices, but whatever there is a method that you'll be able to know the matrices from the equation itself that resembles the same type of character that will resemble the character of this what you can say the function. So from this from this function you will be able to get the matrices that is not the exact same, but we'll be getting a matrices that will represent the same character regarding the definiteness of the function to that of matrices. Okay, so you are able to understand that, right? So can
Yes,
somebody
sir.
tell me how will you get the matrices out of this function? Is there any method that you have read in maths or maybe in the stats? Have you heard about the Hessian matrices?
Hello.
So we are not able to hear you.
Okay.
So
Okay.
we,
Maybe okay. Leave that. First, tell me how will you get to know about the function? Like how will you get the how does that function is behaving without getting the matrices? So for this function itself, how can you say that whether this function is a positive definite or not, or it's a semi definite, or it's a negative definite or negative semi definite? How will you say that? So in the quadratic equation, how generally you say if you have been given a quadratic equation, anything x square plus 2x.
So is it positive definite?
See here the value of x, a, b, and c will define like will tell you whether this function is a positive definite or not. Okay. So for example, if you have a quadratic equation in the form of something like x square plus 2x plus something 5 or 6 or something, anything. So how generally you tell about the function of the quadratic equation? How generally you plot the quadratic equation? To plot the quadratic equation, first you check whether this function is going upward or downward, right?
Yes, sir.
Okay. So
So,
similarly here, if you have been given a, so in the positive definite, you already know the function should be resemble like this. Like for example, for all the values nearby to the minima value. So if you are getting a minima at some point alpha and beta, so neighborhood of that alpha and beta, all the value, if you are just increasing the alpha by delta alpha or maybe beta by delta beta, So the value that you should be getting should be positive, right? So this alpha beta should be the minima of this function to get the positive definite, or to represent any definite or any function upward, right?
Yes, sir.
Okay. So to get any, to know regarding any function, okay, that is not been given in the form of matrices. For the matrices, you can directly calculate the eigenvalues and can say. But for the functions, what you need to see whether this function is going upward or downward. Okay, if this function is going upward, for that, how will you calculate? If you have been given a function fx equals to 0, how will you say whether this function is going upward or downward? You have read calculus, right? How will you say about this function is going, the function is going upward or downward?
So by the
Just tell
sign
me
of the
the
function,
concept that you have used in the calculus to know whether this function is going upward or downward.
so by looking at the sign of the function,
Sign of the function. How will you get to know about the sign of the function? What is that sign of the function?
like it's positive or negative. So,
No, you have to calculate some differentiation, something you need to do, right,
yeah,
to know.
differentiation, sir. Double differentiation.
Okay, before that you have to do something else, to get to know the double differentiation. That before that you have to calculate something else also. You can unmute and can say, so anybody can say what you have to differentiate. Okay, you have to differentiate the function. Okay, so what you have to do that there. So you have a function, you need to be doing the differentiation f dash x of that, and then you need to check whether for the first you have to get the stationary point, right? You have to differentiate the function and equate it to 0 to get the value of all the x where the function is 0, and then you need to double differentiate it and check whether this function is behaving, whether this stationary point or the point that you have got after the differentiating and equating it to 0, what is the value at that point. The double differentiation, after doing the double differentiation, you need to check whether this value is positive or negative, right? And why we are
Yes, sir.
doing that? Double differentiate, why we are double differentiating it and then putting the value and checking whether this value is positive or negative? Why we are doing that?
Sir, if it is like negative, then it's minima, and
No, if
value is
this is a negative, this is a maxima.
yeah, negative, then it's maxima, and it's positive, then it's minima, and if it's zero, then it's saddle point.
Correct. So for this, if you have the function, then what you have to do, you have to first differentiate it, get the stationary point, then double differentiate it, and then check whether this is positive or negative, and then see whether this point is behaving like a minima and maxima. And this is all we are talking about, the local minima and maxima, right? Okay, everybody has got this point. Why we are doing this, and how will you know about the character of the any equation if it has been given in the form of equation and in the form of matrices? Anybody has any doubt in this? Are you guys listening or not?
Yes, sir, we are listening you.
Okay, so tell me how, have you got the concept? How will you calculate? How will you know about the, okay, for if any function is positive definite, what would be the condition for this stuff like that I told you? So what should be the, this should be a minima, right?
Yes, sir.
This should be minima for what? For the positive definite,
Definitely.
correct?
Hmm.
Similarly, if this is a maxima, what is this? This function would be behaving like this, right? This is a maxima.
Positive
Then this will be a
indefinite.
negative definite, right?
Yes, sir. So,
Okay. Any doubt in this till now?
no, sir.
So can we like take an example like function and
Okay, I'll just take the same example that professor has discussed.
yeah. Thank you, sir.
Okay. Okay, or maybe I have a slide. Okay, so see what we have done. Okay, I'll come to that example, but I'll just go through this slide again. I guess that will clarify everything. You're able to see this my screen, right?
Yes, yes, sir.
Huh. So you have a function, right? In the quadratic form, you can write in this form. That is fine. This I haven't talked about how will you write this equation in this matrix form, but that is fine. Till now, this is fine. And then okay. So what you have to do is, if you have the function in the form of quadratic equation, what you will be doing first, you will be partially differentiating, and then you will be getting the first thing that what you have to do is to, if the function is the, because here we are not discussing in the form of only one like dimension, we are just discussing the form of 3D or maybe the 2D form of, like, you have the variable or the equation in the form of x and y. So what you will be doing, you first you need to get the stationary point. Okay, to get the stationary point, you will be partially differentiating first order partial derivative you will be doing with respect to x and y, and then equate it to 0. Both the equation you will be getting the x and y value where the function is 0, right? This is what I've told you. To get the first differentiation, calculate the first differentiation, calculate the stationary point where the function or the slope of that function, whatever we are discussing, is 0. And then you need to check the double differentiation of that function. Okay, so to calculate the double differentiation, what you will be doing, you will be getting a determinant, right? Because this function is the form of it's not in the form of only x or y, this is in the form of x, y both. So you'll be getting the function in this form. So you'll be getting three partial differentiation with respect to one, with respect to xx, then yy, and then xy. Xy or yx is both are same. So you'll be getting a, you can write this in the form of this determinant, and then you need to see whether the determinant is positive or not. Okay. So for the minima, what should be the criteria? So fxx should be greater than 0. That is what, this is the this is the coefficient of x square, right? That is a, correct? And then the determinant should be greater than 0, right? And if this is a maxima, then fxx is less than 0. That means what, the coefficient of x square is negative. That means the function is going downward, right? And then for the saddle point, this is, the determinant is less than 0, and for the and for inconclusive, like, we can't say anything about this function if you are getting the determinant as 0, right? So this is the second partial derivative test. I guess sir has talked or not, I am not pretty sure about this. But whenever you'll go through the lectures, so this should be there in your mind. So I've discussed everything. If you have doubt, you can ask me. I'll just go through some examples also. And for the, yeah, so for the definiteness, this is the all the stuff. So I have told you some other method also. Here I've just written about the if the area that the x transpose ax is mainly the energy that is conserved by that matrix A. This is what, if this is positive, then all the eigen, or you can say with the help of eigen values also. So this is the one method and the other method, but you should not solve with this method. It will take a lot of time. You need to check for each and every x and then check whether this function is behaving positive definite or not. So better to go with eigenvalues or maybe the determinant method, where you'll be calculating the determinant of each, like 1 cross 1, 2 cross 2, 3 cross 3, and see whether you are getting the positive or not. If you are getting all positive, this is positive definite. If you are not getting, then you calculate the eigenvalues and then check how does that function is behaving. Okay. So
Okay,
one
sir.
thing somebody was asking, whether if you are getting a one positive and one negative, then that is an indefinite matrix. Okay, right? Here it has been written, the fifth one, you can see the fifth row, indefinite matrices, where for this matrix you can't say anything about that. Okay, so at some point the eigenvalues are 0, greater than 0, and for some it's less than 0, so that you can't say much about the definiteness. So this is indefinite matrices. Okay, and this is the condition, all the condition that I have written here. And one example you can see it. So here there I have given you one example, 4x square plus 4xy plus 2y square. Okay, without seeing the solution, can somebody tell me whether this function is a positive definite or not?
Yes.
What are the method? What was the method? Check
For
whether the 4 is positive or not, and then check. You can check with the two methods that I have discussed. One, you can calculate. The first thing is the point where the you have to calculate the stationary point, and then calculate the go for the second derivative test, and then you can say that's the one method that you can say. Or maybe you can take out the matrices, and with the matrices you can say, okay, so can somebody solve and tell me whether this function is a positive definite or not?
So,
Huh.
like if we look at the coefficient of x square, then it is positive.
Hmm.
And then we have to solve the determinant. Like, a value is positive 4, and
Hmm.
then 4 into 2 minus that determinant is also coming positive.
So this is what, this is a positive definite,
Positive.
right?
Yes.
Okay, simple.
Yes.
Yeah, so you can say by this method, or you can calculate the this matrix. How will you calculate? See, so this is what, so A is what you have got this, right? So you can get the even the matrices also out of this, like, see, you can calculate the determinant, right? So this is what, this is the same matrices, fxx, fxy, fxy, and fyy. So what you can, if you have a given equation, like I'll just tell you.
So we will be comparing with the general equation, right? Ax square plus 2a
Huh.
2bxy, that way.
See, comparing is a one way. You, after comparing, you'll be getting the exact same matrices. Okay, from the, if you have the function. So what is the function? 4x square plus what was that? Uh,
4xy.
4xy plus 2y square,
2y square.
right?
Yes.
Hmm. So what you can do is you can get the exact same matrices after comparing. Okay, so that's the good one that you have told. So after with the comparing also, so there would be some question where you need to compare and then get the uh, given matrix. Okay, that's the one method. The second method that I'm telling you is the Hessian matrix that you can calculate. How to calculate that, and this Hessian matrix that you are getting, that will also give you the same what you can say, the characteristic of the matrices that from after comparing you'll be getting the same characteristic from the Hessian matrix also. And how will you calculate that? So if you have a if you have the equation in the form of x and y, if this function in the form of x and y, so this is a two variable, right? So what you can do is you can do the partial differentiation with, so you can write it fx here, fy here, fx and fy. So what you have to do, you have to do the function partially, you need to differentiate with respect to x twice. Okay, first you can do with respect to x, and then again with respect to x. So if you are differentiating this, what you will be getting, 8x plus 4y, right? And then again if you are differentiating with respect to x, you'll be getting 8 here, right? Am I correct?
Yes.
Huh. Again you are, and now what you are doing, you have to differentiate with respect to x and then with respect to y. So if you are doing the same step for here, so I have differentiated with respect to x first, and then I need to differentiate with respect to y, so you'll be getting 4 here. Similarly, so this one and this one will be same because this is a symmetric, not this one. Yeah, this one will be same because it's a symmetric matrix, right? Because I told you you'll be getting a symmetric matrix every time. Okay, and if you're not getting symmetric matrix, then you're doing some mistake.
So here will be yx, na? F of yx.
Huh, here this is f of yx. So f of xy or yx both are same. Whether you are differentiating the function first x with respect to x and then with y, or you are doing with respect to y first and then x, you'll be getting the same value. Okay.
Okay, okay, okay.
Hmm. And now the final one is you have to differentiate with respect to y twice. So what the value you'll be getting for this, you'll be getting 0, and then from here you'll 4x and then 4y.
Y.
Again in the end you'll be getting 4.
4.
Now you have got a matrix. And if you are calculating with if you are calculating the character of this matrix, this resemble the same stuffs that you will be getting from this matrices, or maybe from this matrix, or from this function. Okay, so here also I told you how will you calculate. So I told you 3-4 method. The first one is eigenvalues. Okay, you can calculate the eigenvalues also, but here you can go through the some basic other method also that is pretty simpler than that. So what is that? first you need to see whether this is positive or not. I told you first check whether 1 cross 1 is positive or not. That is 1 cross 1, 8 is positive. Similarly, what you can do is now calculate the determinant of this matrix. Is what 32 minus 16 is 16. So that is also positive. So whatever you have told is correct, right? So you have directly you can compare and get the matrices and then tell, or you calculate the Hessian matrix and then tell. Right? Any problem in this question that I've discussed here?
Sir, we will see only first element, right? If that is greater than 0.
No. First element, okay, you need to calculate the determinant also. See, I
Yeah,
told you here, right? Here
yeah,
I
yes,
told you.
sir. We will calculate the determinant that I got, but we have to see the first element also, right?
You need to see the first element also.
If that is greater than 0 or not.
See here, if the determinant is positive and the first element is negative, then you are getting the maxima point. That
Okay,
means
okay,
what?
I
You'll
got
be
it, sir.
getting a different. This is not a positive definite for sure. Okay.
I got it, sir.
Hmm. Or the best method, don't get confused with anything. I told you just calculate if you are getting the function. So I'll tell you for everything. Like if you are not able to understand till now, I'll tell you the one basic approach that you can go through. So if somebody has not understand anything till now, I'll tell you just the two statement. If you are getting anything in the form of matrix, then calculate the eigenvalue and see whether what is that value. If the question in the form of matrix, so there can be two type of question only. Whether the function is given in the form of matrix or in the form of function. So only two things can happen. If this is given in the form of matrix, then calculate the eigenvalue. If the eigenvalue is greater than 0, then this is positive definite. This if this is eigenvalue is greater than equals to 0, then this is a positive semi-definite. And then if the values are, and similarly vice versa, if this is negative, then you can say negative definite. And if this is eigenvalues less than equals to 0, then this is negative semi-definite. Any problem in this? No, right? So this is the one method. If we have got the function, then calculate the Hessian matrix. Hessian matrix, how will you calculate? If you have given the variable in the form of two, like for example, if you have got in the form of f, y, and z, three variable, then what you will do? You will calculate fx, fy, fz, fx, fy, fz. So you will be calculating same function. You will be differentiating with respect to x twice, then xy, then xz. Similarly, yx, y square like means y twice, and then yz, zx, zy, and zz. Right? You will be getting a matrix, and then again you have to do the same steps. Eigenvalue calculate, and you have reached the same here, and then you can calculate and then tell the how does it behave. Is it clear? So you don't have to, if you have been given to calculate the stationary point, then you need to go through the partial difference. If you have been asked to calculate the stationary point, then how will you do that? You just have to calculate the partial differentiation, okay, with respect to x, y, z, like whatever the variable it's been given, and you get it to 0 and calculate the value at what point the function is getting 0, right? And that is the stationary point. And if you have been asked to calculate the double differentiation also, you can do that, right? Is it clear to everyone?
Yes, sir.
Okay, so I guess this okay. So anything else? Any point that you have missed out? If you, now you can just go and watch the whole. Like there are 4 lectures. So last 2 lectures I've discussed everything. The first 2 lectures, I guess in the next session, I guess the Ram will discuss everything. But the last two, I think there won't be any problem if you just go through that one. Okay. Okay. So that is nice. Should I discuss the 7th week PCA part? Are you there or hello? Are you there or not?
We are there.
Yes, sir, we are here, sir.
Okay. So what should I do? Should I move to the seventh week or sixth week? The half part is done.
So can we discuss like the questions of the two lectures that
Okay, I'll just go through the practice and then the graded, or maybe the graded. I'll just discuss the graded questions. How will you go through that?
not
What is
not
the
the
deadline for that?
not a graded, just a
Today,
practice
sir.
For the sixth week?
for the
Yes,
sixth year.
I'd say 8th of March, man.
on for fifth week, sir.
8 March.
Hmm. See, this is a function that x square plus y square. This is pretty simple one. What you have to do is to calculate the stationary point. How will you do that? I told you the partial differentiation with respect to x and then again with respect to y, and then equate it to 0. Solve the equation, you'll get the point where the function is 0, right? Now the second equation is if a has been given, b has been given, then a plus b is a positive definite or not. So how do you do the addition? You just have to add it and see. For the first step should be whether this function is symmetric or not, right? If this is symmetric, for the matrix I told you, how will you do that? You see whether this function. So what was the method I told you? I told you if this is a matrix in given, you calculate the eigenvalues. Or if this is a 2 cross 2 matrix, see, eigenvalues will be calculating for 3 cross 3. Because for 2 cross 2 also you can calculate, but this will take a lot of time. So what you can do is for 2 cross 2, you can first check whether this is positive or not, and then calculate the determinant. If the determinant is positive and this is positive, this is a positive definite, right? So similarly, you can do for the same math. A plus B you do, just check whether the first step, the first one, the A is positive or negative. This is positive, then calculate the determinant. If the determinant is positive, you can directly say whether this is a positive definite or not. Okay. Similarly, for the 3 cross 3 matrix, first check whether this is whether this is symmetric or not. This is symmetric, right? You can see directly. Then what? Then you have to calculate the eigenvalues. Okay, the one method. The second method, what you can do is pivot value. That is going to take a lot of time. The third method is determinant. Check whether, okay, 2 cross 2, 2 is positive. Then check whether this is positive or not. This determinant, 2 cross 2 determinant. So 4 minus 1, this is positive also. Then calculate the determinant of this 3 cross 3. If this is also positive, then you can directly say it's a positive definite. If not, then calculate the eigenvalue and check whether how the values you are getting. If you are getting all the 3 as positive, positive definite. If you are getting even 1 0 and other positive, positive semi-definite. If negative, if you are getting all negative, negative semi-definite. And similarly for the negative definite also.
Can you
Again,
repeat this one, sir? The
which
first
one?
part. The for 3 cross 3 matrix.
For 3 cross 3 matrix, see the best method. So if you are getting confused, the one and the best method is to calculate the eigenvalues. If you are able to calculate eigenvalues, just check whether how that eigenvalue is. If all are positive and greater than 0, you can directly say it's a PD, positive definite. And if you are getting some as 0 and some are positive, you can say positive semi-definite. And similarly for the negative definite also. For this is the simplest method. If you want to do it quickly, what you can do is just check, okay, 2 is positive, 2 cross 2, check the 2 cross 2 matrix. Okay, this is also positive. From here you can directly say 4 minus 1 is positive. Now you have to calculate the 3 cross 3 matrix determinant. If that is positive, you can directly say positive, this is positive definite. If you're not getting, then calculate the eigenvalues and then check. Okay.
Excuse me, sir.
Yeah.
So till now, whenever we found, the eigenvalues for 3 cross 3 matrix,
Mhm.
either like some of the entries were 0. So in that case, the final equation that we got was very easy. But like if you see this matrix, no elements are 0, like, kind of. So we will end up with a, a characteristic equation of order 3, right?
Yeah.
Like lambda raised to 3.
For sure you'll be getting lambda raised to 3.
Okay.
Mhm.
So,
Okay, so if you don't want to calculate eigenvalue, there are other method also.
yeah,
Check for the determinant. Okay.
okay.
Or maybe the pivot value. If you're comfortable to calculate to see the pivot value, that you can do. So there are 2 3 methods, but eigenvalues will give you like the cut like all the method will give you the correct one, but it's like eigenvalues will be much assured
Okay.
method to calculate.
Okay.
Hmm. Similarly, for the fourth one
Ex-
also, you just have to calculate the stationary point. For that, you need to calculate the first order partial derivative and check for the stationary point. The fifth one is a good one. The fifth one, what you have to do is you need to compare and then to compare with the standard like function, and then you need to see. There are other method also that you can use. You can use some tricks to solve this method also, but how will you do that? That I'm not going to say. But one method is to compare and directly say, but the other method is also there to see how will you, like for example, this is z, okay, z square. So for here it is -1. So for all the cases this is -1. What you can do is you can just point out some values that is differentiating with the other, and then check how will you get that. Okay,
Okay, sir.
like for example, this is for the y square, right? This option can't be correct because this value should be representing for the y square. Here y square is positive, here it is negative, so this option can't be correct. So similarly you can eliminate the other options. Did you get the point? How like you'll be able to solve? Or maybe the comparing would be the one method that you can do, but that will take a lot of time to compare because you need to write the general equation, and then for each and every term, because this is a three term, like 3 in the 3 degree, right? In the 2 degree you can directly say, but in the 3 degree it would take a time. So it's better to eliminate the options. So even the first D option, I guess seems to be incorrect because here it is x square, and again you are getting the minus x square from here, right? So I told you like B and D supposed to be incorrect from my point of view. Right. Similarly, you can do for the sixth also, seventh is also the same, eighth is also same, right? All the questions, ninth even is also same. Ninth, so you can directly say, okay, tell me the ninth one. Okay, tell me what is the answer for this ninth one, without solving, without touching the pen and paper.
Positive definite, sir.
How?
For the
Determinant is
first element,
positive.
What is the
For
determinant value here?
2 by 2 determinant have 15 value, and 3 by 3
What is the
will have
eigenvalues for this matrix?
357.
7.
Yeah, 3, 5,
257.
7. All are positive. Is a positive definite, right?
Yeah.
Yes.
And then these two questions will be discussed by Ram. So this is fine. This week got ended, right?
Yeah.
Yeah,
Now
great,
we'll
sir.
move to the seventh. Anything from the sixth week, or should I discuss the practice assignment also?
Let's do it, sir.
Okay. So the same steps you have to do. See, the same thing you have to do 2xy plus y square. What you will do? First, partially differentiate with respect to 2x. So what would be the answer? So please tell me what is the answer for this. So if you will differentiate with respect to, what is that?
XX.
So this is what? 2xy plus y square. If you will
1
differentiate with respect to x, what you will get?
1y square.
2y, right?
Yeah, 2y.
Plus 0. This is respect to x. And with if you are differentiating with respect to y, what will you be getting? 2y
2y.
plus
2x.
2x, right? If you are equating to 0, y equals to what? 0. So you'll be getting what? What is the value you'll be getting?
0.
Tell me. Tell me the answer for this first one.
Can you go to
First
that?
point, we are calculating f double x and double y, right? Hello.
Huh? Yeah.
Double X.
Sir,
Just
we are
need to
finding
yeah,
double x and double y, right?
see, for the stationary point, I told you you have to just calculate, just differentiate, partially differentiate with respect to x, and then the other equation will be with respect to y, and then equate it to 0. You just have to get the stationary point. So for the
Mm-hmm.
double differentiate, so when we do the double differentiation to know regarding the character of that function, for the stationary point you don't have to do the double differentiation, you just have to do the partial differentiation first, like
Partial.
yeah, single. See here, this was the question, right? For the stationary point, what did you do? For first order derivative, you have to calculate first with respect to x and then with respect to y. what you have done, then equate it to 0, you'll be getting, so x 8x plus y 4y equals to 0, 4x plus 4y equals to 0. So two equation, two variable, you'll be solving, you'll be getting the x and y, right, for the stationary point, correct? So similarly here you'll
Got
be doing the same steps.
got
Okay.
it, sir.
So what is the value you
Should
are
we try?
getting, x and y? Okay, calculate, and just take 2 minutes and calculate this question.
0, 0.
Yeah, you'll be getting 0, 0. Okay, so do this question, second one, the matrix, this one, and tell me whether this matrix is positive definite or not. If you'll not get, I'll solve this problem. So I'll just giving you 2 minutes to solve this, otherwise I'll solve this. Okay, how many of think that this is a positive definite? So what is the eigenvalue that you have got? I guess this is a positive definite itself, like this is a positive definite or not, let me take. Yeah, this is a positive definite. So you are getting, so 4 is positive, right? And then 4 into 2 minus 1 is 7. That is also positive. And then you need just have to calculate the eigenvalue of the, like the determinant of the 3 cross 3. So you'll be getting positive, that also positive. Right? Any problem in this, solving this problem? The
So I
second
have
one?
a doubt.
Huh?
So by determinant, we can like say it is positive, but like if it is positive semi-definite, then in that case, one of the determinant will come zero.
Yeah, correct.
How? Okay, okay. One of the I'm asking.
Sir, can you
Hmm.
do this?
Okay.
Can you do this?
So just tell me the values.
Row wise.
Hmm.
4 1 minus 1.
Okay. So this is 4, 1.
1 minus 1.
Okay.
1 1.
1, 1.
1 2 1.
1 to 1.
Minus 1 1 2.
Hmm. See, so what you can do is the first method you can calculate the eigenvalues, that I'm not discuss here. Like, that will take time. So the better method here is, you can see this 4 is a positive. 4 is positive. That means the 1 cross 1, that is positive. 4 is greater than 0. Then the 2 cross 2 matrix, that is 4 into 2 minus 1, that is 7, is greater than 0. The third matrix, the 2 cross 2 is also positive. The third is, how will you calculate that? 4 into, you just erase this one. So you'll be getting what? 4 minus 1. Minus 1. Then you can erase this one, and then 2 minus of minus 1, that is positive. And then you have minus 1, and that is how much you're getting. This is 1 of minus 2. So you're getting how much? 4 into 3 is 12, minus 3 minus 3. So that is equals to 6. That is also positive. So you're getting all the 3 as positive. So this is a positive definite matrix. Right? Any confusion in this?
No, sir.
Okay, you'll be able to do that.
Okay,
So that
so first we will see the first element. If that is greater than 0, then we will check for 2 cross 2.
huh. See, but the problem here is if you're getting for something is negative. So there are the method that I'm not telling you because that will make you a lot of confusion. Okay. So if you are getting anything negative, okay, so the best method is to go and calculate the eigenvalues. So that's why I'm from the starting I'm telling you eigenvalue to calculate the eigenvalue. That is the best one of the best method to calculate. Okay.
Okay,
If you are
sir.
getting negative, some negative, so that thing I'm not telling you how to get whether if like for example here you are getting the negative for 2 cross 2, for 1 cross 1 you got the positive, for 2 cross 2 you got getting negative. So from there are like 2 3 again stuff that you need to remember. Okay, like you will be getting odd negative or even negative or odd positive even positive. So that I'm not telling you because that will make you a lot of confusion. So if you are getting anything negative, just calculate the eigenvalues and see whether this is a positive or negative. That's the best method to calculate. Okay, fine.
Okay, sir. Okay, yes,
Hmm.
sir.
Any confusion you can ask me now itself. So there will be some like 2 3 questions in the quiz also, so that you should not be making any mistake. The quiz 2 will be a bit on the tougher side because there are some portion that is a bit tougher. Okay, at least the bit tougher than the week 1 to 4. So whatever the portion that is not that difficult, you should be making it correct. So fifth week, all the questions you should be making correct because fifth week is like the simpler of all the 4 week that you'll be going through. So fifth week you'll be getting the problem like 4 problem from each week. So 2 problems will be there from this portion also, and two portion from the SBD. And SBD is also a simpler one. You can see that you can think of this as a difficult portion, but you'll be getting the question pretty simple from the SBD because we can't give any difficult question from the SBD part also because you'll be getting a simpler question also. That I'll tell you in the revision session. How will you get a? There are some 2 3 tricks that you can solve directly the SBD portion. Okay, but after going through the whole the first calculate the basic approach also, and then we'll discuss the SBD part also later. Okay, so this person should not be making any mistake in the exam. Okay, is correct. Like it's fine, right? Can we move to the next portion? Next questions.
Sure, sir.
Any doubt you can just ask me. So the third one you can directly say, right, without calculating. Just tell me whether it's a positive definite or not. So I'm just like, can somebody tell me whether this is like the answer is already given? Can somebody tell me whether why this is a positive definite?
Yes, sir. It is positive definite because the first element is greater than 0 and the determinant is also greater than 0. 2.
Hmm. Right? Okay, tell me about this one. Calculate the stationary point for this matrix. How will you calculate for this matrices? Okay, tell me the approach. How will you go through that? How will you calculate the stationary point for this equation?
Sir, we have to find the partial derivation with respect to x and y, and then equate
Equate it to 0.
both the equation to the 0,
Yeah, that's the correct approach. First, do
and then
the
find the value of x and y, and that is the
huh,
stationary point.
correct. Nice. Uh, okay. Okay, tell me for this question without using the method of that comparison and all. Just go through the options and the problem. So the same problem is there in the graded also. Similar type of problem, not the exact same, but similar problem you have.
Fourth one,
Which one?
fourth option.
Fourth option. I guess here you are correct. Okay. How did you do that? I guess you have seen the
Y
y square,
square.
right?
Y square, yeah.
Huh. So there is no y square in this matrix, and there here also there is no y square. So you can directly say this is the correct option because in every all the other option, this option is not prepared correct. Like in the it's made in such a way that you can directly say without even solving. Right? Any problem? Anybody is having?
No, sir.
Hmm. Similarly, okay. So, okay, tell me how will you say about this whether it's a minimum, maximum, or saddle point? For this, you need to go through the
Double
second
derivation.
derivative test, right?
Double derivation, right, sir?
हाँ वही हाँ ठीक है तो what you'll do you'll just calculate x and y where the stationary points already given. You just need to calculate the partial double differentiation and then check whether this function is a maximum or minimum. Similarly, for this matrix, this is not positive definite because the determinant you are getting as a negative. So this for this you can't say anything. So it's neither positive definite nor positive semi definite. Okay, what is the eigenvalue for this matrix?
-6, -5, -7.
So this is a negative definite, right?
Perfect.
Okay. So this is all. So this is what I was telling you, the SVD part that we will be discussing. But this also will be getting a simple question. So this looks a bigger question, like it's a bit difficult, but there are methods that you can solve it with, like in a 1 minute or maybe a 2 minute. Okay. So this is done. So can I move to the seventh week? This week, I guess the portion that I need to cover is like clear. I guess the other part will be discussed later. Should I move to the next week, seventh week, or can we close this?
7 weeks, sir.
Okay, so I'll just discuss the brief idea. I'll give you the brief idea of the seventh week. Okay. Yeah.
Yeah, because we have only 17 minutes.
What?
Because we have a very less time, sir.
I'll just discuss the idea. Give you the brief idea. I'll discuss it again in the next week. Okay. The same steps stuff I'll again discuss. So I'll just give you a basic idea. So can somebody tell me, have anybody has went through this concept PCA, principal component analysis? What is that? What generally we do with this method PCA? See, it's written here for the first method. The why we are doing PCA is the principal component analysis for the visualization purposes. Like in the ML problem, if you have a data, if you have a data set and that data set is consist of, like for example, 1,000 features. Okay, if you have the 1,000 features, how will you how will you visualize those features? Because you can't visualize. You can maximum visualize with the if you have features in 2 dimension or 3 dimension maximum. Okay, so what you'll do is from the 1,000 dimension you need to come to the 2 dimension, right? 2 or 3 dimension to just visualize how does it look, the data set whatever you have, how does that look? Okay, so there is a method that is called PCA, principal component analysis. That with that method you can you'll be able to visualize without losing much of the information. You'll be losing the information but not much. Okay, so how will you do that? That will be going through this method. Okay, so the training data set that is been given, so we'll be converting this into a D dash from a D, like that is a D dimension, and D dimension is like a very bigger one. So D dimension is very big, means like your features is like very large, like 1,000 dimension, and then you are coming to the 2 dimension and 3 dimension. What is the geometrical intuition or the intuition of that? So for example, you have a two features of a matrix. Like you have a data set that has been given to you, your data scientist, and then you have been given features like the like the features of 1,000 people, and that 1,000 people, and that two features has what you need to predict the weight of the person, and you have the features like the blackness of the hair and the height of the person. Okay, so if you have 1,000 feature, 1,000 like this example is like 2 dimension because it's a two feature. So 2 dimension you need to convert from 2 dimension to 1 dimension, and similarly you'll be doing for the 1,000 dimension. From the 1,000 dimension you'll be using the same step to convert it to the 2 dimension. Okay, so I'm just giving you an example. From the 2 dimension you need to come to 1 dimension, right? So the two features are what? So from the here, what are the two features that I told you? What is the feature here? The height and the blackness of the hair, right?
Yes, sir.
Yes, sir.
Correct. And from these two features, you need to calculate the weight of the person. right? So you can see the, so when you have plotted the data set, whatever you have been given from the two features, you have plotted here. Okay, what you have to do is you have to come from this two dimension to the one dimension, right? And that you are doing with the help of PCA. So how does that PCA, that I'm telling you, not the exact way, but I'm just telling you a, giving a brief idea how does that generally works to convert it from two dimension to one dimension. So the spreadness, you can see spreadness is like the variability of the data. So the blackness of the hair, you can see, you can imagine in, if you are if you are collecting the data of the Indian people, like in Indian people, so you can say the hair color of the people belonging to India mostly really from what, like will be a black gray to the black, right? So if you are just converting this black value, you're giving a mathematical value to the black, that will be one, right? For the gray it will be one, what, from 0.095 to the one, right? But the height will vary a lot, like a lot, right? Not a lot, but the height will be like from the 4 feet to something like 7 or 7.5. So the height, the variability or the spreadness in the height would be a very large as respect to the blackness of the hair. Are you agreeing with me or not?
So can you please repeat?
Okay, I'll repeat it. We have a data set. The data set consists of 1,000 data point, right? And each data point has two features, and the one feature is the blackness of the hair. Blackness of the hair means how gray or how black that his hair is, and the height of the people. Okay, the height of the feature is, let's for example, it's measured in some centimeter, and that height is yeah, it's measured in the centimeter, and the blackness is on the basis of color. We are converting that color in some mathematical value, and that mathematical value is from, for the white, for the exact totally white we are giving 0, and for the black we are giving 1. Okay, so mostly the people will be what, gray value, right? The gray or black. So the gray we are giving 0.95, and then the black is like 1. So the value of this feature, the f1, that is the blackness of the hair, will vary very less, right?
Because the difference between 1 and 0.5 is very less.
Yeah, correct. Because the hair color of the people belonging to India will be mostly black, right?
Okay.
Right. So and now from this feature I need to predict the weight of that person. So do you think this f1 will help you in predicting the weight of the person, or height will be giving you a get a like, what you can say, the idea? Which one will give you get an idea, which will help your model to give you the weight of that person, the height of the blackness of the hair from this data that I have like shown to you, this this data set that I told you,
Height, sir.
Height, sir, height.
right? Why height?
Because it's possible that
No, see, you don't have to think much. From this data, tell me, like the spreadness is very less in the blackness, right? Because almost all the people has the same label of this value, f1 feature. If one feature is almost same, right, this feature can be, this is redundant, right? This we can remove. Even if you are removing f1 and just on the base, I'm giving this f2 only for the model, that is not going to make our model bad, right?
yes, sir.
If I'm removing this f1 and just keeping f2, right? So that we are not removing, or we are not
Dependent, sir.
losing much of the information. Our model will be as good as the, with the help of f1 f2, because f1 every time I'm getting the same value, almost 1, right? Like for
Yes, sir.
example, if the model is something like m1 x1 plus m2 x2, and x2 is what, x2 is for the height, f2 features, and f1. So m1 x1, so every time I'm putting the same x1, right, almost 1, and this is m1, so this will work like a some constant value, right?
Yes, sir.
If this is working like a constant value, and then I need to predict some value like weight of the person, every time this is going to help to build a model, better model. This is not going to help. because
Yes, sir.
this is almost same every time, right? So this is redundant. So I can directly convert this 2D into 1D by removing this f1.
Yes,
Is
sir.
this
We can
clear?
say that F1 is not dependent.
F1 is not helping at all to measure the weight of the person, right? Because the spreadness is very less.
Mm.
Spreadness means for this is like, for example, this is F1 and this is F2. And if the data is like this, every data is like on the same pace. So that means what? Every time F1 is same, F2 is only varying. And if F2 is varying, that means what? F2 is only helping me to build the model to get the weight of the person. F1 is not helping me. Is this till now? Is it clear, everyone?
Yes, sir.
Yes.
Other people tell me. Is it clear?
Yes,
Yes.
sir.
Hmm. So if 2D, so have you understood like from 2D how will you convert to 1D? So in the similar way we can convert, right? We can convert from 100 dimension also. Like if I have a features 100 features, and if you are able to calculate the correlation within the function, the relation the features, and many of the function maybe it's like totally correlated, or maybe some are like, if some like two functions are totally correlated, we can replace two features with one, right? Correct.
Correct, sir.
Hmm. So here we have converted, we have learned how to go from two dimensional to one dimensional. Similarly, we'll see how will you convert from some bigger dimension to the lesser dimension. Okay, and that I'll discuss you in the maybe the upcoming session, that next session. And week 7 is like, I guess, when is the deadline for that?
We have a long
19
time,
for
sir.
week 7.
19.
Okay, so we will discuss this week nicely. Okay, so I guess the very basic idea, I guess you have got how you have converting from 2D to 1D. Later part with the mathematical term, we'll see how will you convert from some bigger dimension, from thousand of dimension to some 3 to 4 dimension, and then we'll see how will we visualize those portions and all. Okay, so is it clear, sir? All the stuff that I've discussed today.
Yes, sir.
So will it be like related to dimensional reduction that we did in the first week,
Yeah, correct. This is similar to that one.
where we used encoder and decoder?
Correct, correct.
Okay.
This is the same step that, yeah. This is the unsupervised learning. Yeah.
Yeah.
I hope this session helped you. If you have any doubt, you can just ask me. Hmm? You have any doubt, you can just ask me now. Hmm? Do you have any doubts?
No, sir. I
Anyone?
think everything is clear.
Okay. So any doubt, you can just mail me, or maybe you can just post into the discourse, or if you are mailing me, you can just mail me. I'll just reply on there. Okay.
So just one request.
Hmm.
Actually, most of the MLF classes are clashing with math classes.
But maths, very few people would have taken maths and MLF both at the same time, right?
Yeah, I don't know, sir, but like mostly the classes are clashing, and we have to like select one of the two and attend. Is it possible? Like, can you consider this and make changes?
Uh, like, see, the problem, like maths is like in the foundation, I guess. So
Mm-hmm.
we have already taken into this consideration that the maths course, okay, but this I can't tell you for the confirm. But one thing I can tell you, if you have doubt, you can just post like, uh, you can just mail me, and then I'll helping you for sure. Okay, that I'll make sure. But this session I can't give you a guarantee that it will be, because it's already like sixth week is done, right?
Yeah, and both the days on Tuesdays and Thursdays, both the days they are clashing. It's not like one off
It's
day.
not a Tuesday. Then one is Thursday, right? One is Thursday and one is Saturday.
There
Uh,
was a
no, sir.
Tuesday.
We have on Tuesday and Thursday also. I also have the problem, sir.
Yeah, Tuesday I guess this week only has happened because of the live, like because of the quiz. So we have taken one extra session this week.
So in the calendar, it's like that. If you can allow me to share the calendar, I can show you.
You can share the
Like
calendar.
for every week, 8 to 10 p.m. on Tuesday, and let me share. Second. So the 8 to 10 p.m. Tuesday and Thursday. Maths
Yeah,
2 and
Thursday is there. Thursday I can see. Thursday and Saturday,
okay.
right?
No, sir, they had added
Thursday
3
and
classes
Tuesday.
per week, sir, of MLF.
Tuesday.
Fifth also on fifth.
Hmm?
So on
So
fifth.
they added 3 classes per week for MLF.
Okay.
Tuesday, Thursday, Saturday.
Sorry, seventh. I can see seventh. On seventh also we have
7th and 9th.
The
Similarly,
seventh,
next
okay, seventh is. So this is
this
maths
will
1 or
be
maths 2?
maths too. Yeah.
yes. On 16th also it's like that.
So how many people? I guess there are not much people who is facing this problem. See, the problem, if I'm saved to some other, it will clash with some other courses also.
Yeah. We can understand. So, but at least if you change on only one session, like
So Saturday 4 to 6, you have anything?
no, this session was not clashing with anything else.
This session
4
was
to
not
6,
classic.
but it can clash with some other people, right?
Mm.
Okay, so one session that is Saturday 4 to 6. I'll just ask Narayanan if nobody is having that session, I'll just shift this Saturday. Thursday I can't do much.
Today's session was had no problem. 2 to
No
4
problem.
was
Okay,
yeah.
2 to 4 there is no session, right? So you have a
No,
Yes.
problem with Thursday and Tuesday,
for
right?
all.
Tuesday. Yes. Tuesdays and Thursdays.
Hmm.
This one.
Again, ask the maths team, but I'm not pretty sure whether they'll consider or not because I need to ask again Ram. One thing you can do next session, Ram, you can also say about I'll
Okay.
ask Ram.
We have raised this with Max team also. And
Huh?
I've also wrote to the support team.
Okay.
So
So no, didn't got any reply, right?
yes, yes. This
Okay.
problem is not
Okay, I'll
solved yet.
talk to Shubham. Shubham is there in the maths, right?
We're not sure, sir.
Shubhashish and Shubhajit.
Okay.
Sushmita ma'am.
Hmm. Okay. Okay, I'll talk to them once. If that is fine, I'll shift it to some other session.
At
But
least one day. At least one day will help.
Just one, yeah.
okay. Okay, I'll discuss with Ram also about this. I'll try to help it out. Okay.
Thank you. Thank you, sir.
Thank you so much.
Okay. Okay. Thanks everyone. I hope this session helped you. So
Yes, sir, of course.
okay. Fine. Then should I close the session or
Yes.
Yes, sir.
Thank you.
Thank you, sir.
thanks everyone for joining the session.